Hello, everybody. My name is Qing Yang. I'm SASS Ph.D. candidate in University of Georgia. Today, I will introduce my paper, Self-Adaptive Swarm System, SASS, which is also my PhD thesis. And I will separate 5 parts to introduce this paper. First, let us have some background knowledge about this research. So actually, the real world, even the whole universe, can be regarded as a distributed intelligence system. Generally speaking, they can classify as two kinds of systems. The natural systems include all the living beings and creatures. Artificial systems like robot agents, software entity, and stuff like that. They are characterized by apparently complex behavior that emerge as a result of the often nonlinear spatial-temporal interactions among a large number of the components at different levels of organizations. So the right picture, I just give you several examples about different situations. It also has some fundamental questions in this research area. First, what is the complexity? The other is what is intelligence? So from the system theory's perspective, the interaction building certain relationship between and within various elements of the system can be regarded as a complexity. From an individual's angle, agent or element principle acting might lead to system behavior and inner relationship changing. So from our studies, intelligence can be regarded as the global adaptive behaviors caused by the individual agent's interaction and cooperation, building the complex and organized relationships based on its current needs or the entire system utility in the specific scenarios. Especially the distributed artificial intelligence (DAI) is a subfield of AI which is concerned with the system that consists of multiple independent entities that interact in a domain. It has been divided into two subdisciplines: distributed problem solving (DPS), multi-agent system (MAS). So for the multi-agent system, it's a very abstract idea. They consist of a number of the agents which interact with each other, and the agent will act on behalf of the users with different goals and motivations. They will require the ability to cooperate, coordinate, and negotiate with each other, much as people do. From applications perspective, especially multi-robot system (MRS), one important way to view the domain space in DAI is by understanding the types of the interactions that can take place between the entity in the system. The common forms of the interaction in MRS are collective, cooperative, collaborative, coordinative. Let us briefly review some related work. For cooperative MAS, the individual is aware of the other group's member and actively share and integrates its needs, goals, actions, plans, and strategy to achieve a common goal and benefit the entire group. It can maximize global system utility and guarantee a sustainable development for each group member. For low-level MRS planning and control, recent research focuses on navigation and formation control programs, especially from swarm robotics perspective. It emphasizes a large number of agents and promotes scalability, for instance, by using local communication. For high-level MAS decision-making and learning, the study implements Markov decision process, MDP, and its variants, game theoretic method, and swarm intelligence. More specifically, for MAS cooperative working in adversary environments, most of the past and current research focus on the unintentional adversary in the environment, such as path planning avoid static or dynamic obstacles and formation control avoid collisions. This research wants to solve several problems. First, we want to develop a more advanced MAS framework by integrating the fourth level of the autonomous system, by combining task decomposition, group formation, planning and control, and high-level decision-making and learning. Then, it is essential to develop an approach to organizing agents' behavior and optimizing or sub-optimizing the system utility, considering building deeper cooperative relationships among the agents representing more complex cooperative strategy with higher success probability and lower cost in uncertain and adversary environments. Last, for MAS cooperative working in uncertain and adversary environments, it is more realistic and practical to build a reliable and stable trust network, organizing agents' behaviors, balancing their needs, solving conflicts, and getting system strategy consensus to achieve the common goal. The third part, we will briefly discuss the system design. So generally speaking, we propose a new heterogeneous MAS cooperation architecture, self-adaptive swarm system, SASS, which integrates the perception, communication, decision-making, learning, planning, and execution to address the fourth level of the autonomous system gaps. The left picture just represents the entire process as a behavior tree. This graph just represents the SASS synthetic framework. From individual's angle, they have two modules, perception and the task component. Using the observing data, like the distance, speed, and image, stuff like that. Through the perception, they can get the specific output predicting data. Then using the predicting data through the task component, they can get the suitable strategy combination to adapt the current situation. From system perspective, we build a trust network we call relative needs entropy network to help agents negotiation and get a consensus to achieve the common goal. This research has several contributions. First, we build a robust needs hierarchy inspired by Maslow's hierarchy of human needs, which can model the individual's motivation in the negotiation process, helping AI agents like robots, corporations, and human and AI agents corporations. Then, in order to solve the conflicts between agents corporation, we propose a distributed negotiation and agreement mechanism based on the robust needs priority queue mechanism. We also provide some autumn operation to decompose the group behavior into a series of simple behavior, like selection, formation, depending on specific scenario, routine, achieving the complex task recursively. Next, we build a new network model, game theoretic utility tree, GUTS, to achieve heterogeneous MAS, high-level cooperative decision-making and learning in adversary or complex environments. In order to help agents negotiation, solving conflicts, and get a consensus, we build a new agent trust model, relative needs entropy, from information and statistic theories perspective. Finally, we implement our idea in explorer alien games and urban search and rescue missions. The first part, we will briefly discuss our research progress. First, we simulated the SASS low-level planning and control. In this simulation, we only considered lower three levels needs, safety needs, basic needs, and capability needs in the robust needs hierarchy. This table just represents the entire process detail. This graph illustrates the task decomposition through planning at selection, formation, and routine phases with 12 robots and 3 tasks. This is the video of the simulation. So first, we simulated the static task, same initial energy level cost robot with 5 different priority, and we simulated different initial energy level cost robots. Also, we simulated scalability and complexity with the lower energy level. Then we compare different order of the task priority and consider with and without collision. Next, we simulate the game theoretic utility tree, GUTS. So in this research, we choose Unity game engine to simulate the Explorer and Alien games, and select the Gamebit toolkit for calculating corresponding Nash equivalence. This first picture represents the game scenario while aliens block the path to a target of the explorers. This is the simulation video. So first, we simulated the self-interest scenario. And we compiled state-of-art QMix algorithms. And consider the partial cooperation. And consider collaborative rationalities. Yeah, we also consider the unintentional adversary, the mountain. And last, we consider the most complex scenario in the last simulation. Then, we build a simple scenario in urban search and rescue mission to analyze the performance of needs-driven heterogeneous multi-robots cooperation. Those pictures just represent the first scenario with homogeneous and heterogeneous teams of carrier and observer in a rescue mission simulation. This is the video of the simulation. As you can see, we first consider homogeneous robots groups, the carriers, and analyze the performance, like the number of the rescued object, number of the recharge round, groups, energy cost, stuff like that. Then we simulate the observers, also the homogeneous robots group. And we simulate the heterogeneous groups with carrier and observer. Compare with the homogeneous groups performance. Then, in order to help multi-agent interaction and cooperation, we build a new agent trust model, relative needs entropy, and implement it in a more complex urban search and rescue mission. This picture just illustrates two heterogeneous robots teams, ground robots plus the aerial robots, cooperatively achieving tasks of two difficulty levels in a post-nuclear leak rescue mission. This is the video of the simulation. So in this scenario, we consider 2 observer, 4 supplier, 6 carrier, separated into 2 groups, executing 2 different missions. One is the challenging one, the other is the easy one. And we also consider the unintentional adversary, like the radioactive resources and obstacles. We analyze in a limited time how much victim they can rescue and compel their energy and HP cost with other state-of-art methods. And every time they back to the initial position, they will regroup based on their current needs level. So for the last part, I will briefly discuss our further works. For our previous work, we built a novel heterogeneous MAS cooperation architecture, SASS, based on robust needs hierarchy, and we also create a trust network, RNE network, to help agents better understand and interact with each other in their cooperation. So for the future work, we will finish our SASS synthetic framework, especially for the high-level learning part, design the appropriate trust RNE network and building suitable perception models and task components model especially simplified gas model, stuff like that. Okay, thank you very much. This is my paper representation.